you work at the board, you work coding things up, etc. And then suddenly you have an epiphany. My name is Charles Leiserson. I'm Professor of Computer Science and Engineering in the Computer Science and Artificial Intelligence Laboratory at MIT.
Broadly, the Supertech group does research in parallel computing and software performance engineering. And it's a somewhat unique group in spanning both theory and practice. We care about not only making things that have good theoretical properties, that offer guarantees of, say, performing well, but in fact can be implemented and run on real computers.
And so one thing that Supertech does research on is how to use math to prove things can be done in parallel. And then to make it easy for programmers to know if things can be done in parallel. And then to make it easy for them to do things in parallel at the same time.
There's a lot of good reasons why we would like to have code that is efficient. That's particularly true given the end of Moore's law, where hardware efficiencies are no longer increasing at the rate that they used to.
There's a popular conception of Moore's law, which you might find around, which is basically that computers get better or faster over time. That's a popular conception which is driven, or has historically been driven, by a technological trend relating to semiconductors and miniaturization, where the number of transistors you can fit in a given area of silicon has historically doubled roughly every 2 years.
The transistor is like this tiny component of every computer chip that's like the backbone of every computation. And historically, we've been able to say that computers are going to get faster because we can fit more of these little guys onto a chip. The thing is, we've gotten to the point where these transistors are so small that they physically can't get any smaller. We're reaching the point where there's quantum entanglement happening to the point that we can't make them any smaller. And so, the need for data and the need for high processing is not going to stop. We're going to need to keep getting more powerful. All of a sudden, we can't rely on this easy way out anymore.
That was like a massive printing press for performance, the thing that we need, and we've been able to build up things. But now that Moore's law is over, we're kind of on fixed income. Now it makes a lot of sense to look at the other side of the equation and try to cut costs. And that's what we're doing with software performance engineering.
So imagine I had 10 apples, right? And I had a bunch of people that could eat these apples. Theoretically, the more people you had to eat these apples, the faster you could eat all of them. So if I had 10 apples in one person, then it would take a long time because that person would have to eat all 10 of them. But if I had 10 people, maybe each one could eat one apple and it would be done fast. And so the idea of parallel computing is if you have a bunch of tasks to do and you also have a lot of processors, computational units or computers, you could have them work together and get things done faster.
Right now, you can get fast code if you're willing to sweat the details, but not everybody in the world can do that. So my thought was, I like when we democratize technology, I'm focused on how do you make it so that average programmers and expert programmers alike can produce more efficient, fast code. And so we, day to day, look at ways that we can make it easy for people to improve performance. So we both work on how do you make specific kinds of code go faster. We also work on the tools that allow anybody to generate fast code for themselves.
You want people to be able to write software that's still maintainable and readable and debuggable, but gets great performance on modern day hardware. And in order to facilitate that, the systems work that we do in Supertech is really vital.
Parallel computing is kind of more in vogue now. A lot of new programming languages come with a lot of these constructs to do this parallel computing work a lot easier. But C and C++ are old languages, but they don't come with these parallel constructs by default, right? They're older. They're from a time when we didn't really care about this parallelization of code. And so what we're allowing programmers to do is to take these old languages and install these parallel constructs without having to rewrite everything else, in such a way that all the behavior is consistent, things just get a lot faster. And so when you're working on a legacy system, which could be any software that you use on a day-to-day basis, all of a sudden there's an opportunity that it gets much faster and you're able to do things a lot better. We're already doing work to look at how we can explore making these training processes so much faster. I would say that I hope the public is excited.
With the end of Moore's law, we don't have other options. People can talk about things like quantum or neuromorphic computing or what have you, But still, it all comes down to, can you get software that's going to exploit whatever technology you're going to use efficiently. With the AI revolution, it is particularly important to try to make our systems be efficient.
And that's why this research that we're doing right now, like, we're at a tipping point where it's going to be like the next generation of how we continue to make progress in computing. And so if you want to be part of that next generation and building it, like, this is the lab to do it.